In the spring of 1968, a structural steel firm in Chicago received a set of drawings that did not look like anything it had built before. The company made heavy industrial weldments, girders, bridge sections. The kind of steel that holds up buildings and mine head frames and machinery too large to move once it is bolted down. What landed on the drafting table was a single welded frame 98 feet long with mounting pads running the whole way down it and a fuel tank designed into the structure itself. It was the backbone of a locomotive, and it had been sent to a bridge shop for one reason. The company that ordered it, the largest and most successful locomotive builder in the world, could not fit it inside its own factory. Sit with that for a second. The dominant manufacturer of American diesel locomotives had been asked to build a machine so long that its own assembly building could not accept the first piece of it. Every trend in the industry at that moment said this was a mistake. The horsepower race was ending. The market was standardizing. Railroads were being told to stop designing locomotives and start buying them off a catalog like everyone else. One railroad refused, and the man who forced the issue would be pushed out of his job before the last unit was delivered. So why did Union Pacific spend a fortune building a locomotive the rest of the industry had already written off? The answer is not stubbornness, and it is not nostalgia. It comes down to a specific operating problem, a decade of expensive failures, and one argument about horsepower that nobody had won yet. Start with the geography, because the geography is the whole reason this machine exists. Union Pacific's core route ran west out of Nebraska across Wyoming and into Utah, then split toward Southern California and the Pacific Northwest. Long distances, wide open country. Grades that were real but not brutal, at least compared to what railroads on the coast were fighting. And crucially, the railroad's most profitable traffic in that era was not coal or grain. It was time-sensitive merchandise. Manufactured goods, parcels, produce, the kind of freight that pays a premium because it has to be somewhere by a certain hour. That traffic was fought over. Competing railroads ran parallel routes to the same coastal markets, and some of them had shorter mileage. Union Pacific's answer was speed. If the route was longer, the train had to be faster. Speed on a railroad is not really about top speed. It is about horsepower per ton and about how quickly you can recover the time you lose. Every curve with a restriction, every slow order over rough track, every station stop and signal check bleeds minutes off a schedule. A train that accelerates hard out of those restrictions makes the time back. A train that lumbers back up to track speed does not. So the railroad wanted horsepower. A lot of it concentrated in as few units as possible. Why not simply couple more locomotives together? Because in that era, every additional unit carried its own overhead, its own set of filters and lube oil and air compressor, its own inspection cycle, its own place in the shop queue. The theory in the motive power department was straightforward. Replace a string of tired first-generation units with a handful of enormous ones and you cut maintenance labor, parts inventory, and fuel handling all at once. It was a clean idea on paper. On steel, it kept failing. By the middle of the 1960s, Union Pacific had already run the most ambitious high-horsepower experiment in North American railroading, and most of it had ended badly. The railroad had spent nearly 2 decades operating gas turbine locomotives. These were genuinely extraordinary machines, burning heavy residual oil in a jet engine driving a generator, and the largest of them produced more power than anything else on rails. They also drank fuel at an alarming rate whenever they were not working hard. They were deafening, and they were so specialized that only one railroad in the world found them worth the trouble. By the end of the decade, they were being cut up. Then came the double diesels. In the early 60s, the railroad effectively ran a competition among the 3 remaining American builders, asking each of them to put 2 engines on one frame. All 3 said yes. The results were a study in disappointment. One builder delivered a twin-engine unit built from the guts of its standard road switcher, and those units struggled with reliability and were retired after roughly a decade. Another builder, already in serious commercial trouble, produced 3 units rated at 5,500 horsepower. On paper, they were the most powerful diesel locomotives on Earth. In service, they suffered chronic electrical problems, including fires traced to wiring that could not handle the loads being asked of it. All 3 were scrapped after about 6 years. Only one builder came out of that round with anything resembling success, and even that success was partial. Its double unit worked well enough to justify a follow-up order, but it was essentially 2 existing locomotives sharing a frame, with the compromises that implies. By 1968, the conclusion across the industry was obvious to almost everybody. Multi-engine locomotives were a dead end. They cost more to maintain, they were harder to work on, and when one half of the machine failed, you were dragging the other half around as expensive ballast. The future belonged to standardized single-engine units built in volume, ordered from a catalog, interchangeable across the continent. Almost everybody agreed. Union Pacific's chief mechanical officer did not. David Newhart ran the railroad's motive power and machinery department, and by every account, he was a difficult man to argue with. He had been the driving force behind the double diesel competition in the first place. He had strong opinions about which builders could be trusted and which could not. And he held a view that was rapidly becoming heresy in his own industry, which was that a railroad ought to specify its own locomotives rather than accept whatever the manufacturer chose to sell. In March of 1968, he opened a conversation with the builder that had come closest to getting it right. He did not want a slightly improved version of the previous machine. He wanted a locomotive that would fix everything the earlier attempts had gotten wrong. 13 months later, the first one was finished. That timeline is the part that still startles engineers. 13 months from the opening conversation to a delivered running locomotive of a type that had never existed, with a frame no locomotive plant in the country could fabricate. And it was rushed at the end for a reason that had nothing to do with engineering. May the 10th, 1969 was the 100th anniversary of the driving of the Golden Spike in Utah, the ceremony that completed the first transcontinental railroad. The railroad wanted its new machine standing in the sun on that day. The builder pushed the first unit out early. It hauled the commemorative train west, and it rolled into Salt Lake City on the morning of the anniversary. The class got its name from that date. The whole fleet was numbered in the 6900s for the same reason. 47 were eventually built, and no other railroad ever bought one. So what was actually inside it? Two 16-cylinder engines, each rated at 3,300 horsepower, mounted end-to-end on that single fabricated frame, with the radiators flaring out at the middle and a walkway threading between the two engine rooms. 6,600 horsepower in one unit. Two 4-axle trucks, every axle powered. 8 traction motors on the ground. Fully fueled, it weighed roughly 270 tons. The fuel tank alone held more than 8,000 gallons, which was more than any diesel locomotive had ever carried, and which meant that a full tank weighed about as much as a loaded boxcar. But the raw numbers were never the interesting part, and this is where the story turns. Because the railroad had not asked for a bigger locomotive, it had asked for a better one, and the specification list ran to 14 separate improvements that the chief mechanical officer laid out in a speech that autumn. Some of them were small comforts that tell you a lot about what the shop floor had been complaining about. Heated windshields. A handbrake moved inside the cab so nobody had to climb around on an icy walkway to set it. Unitized air brake components. A stronger pilot. 2 of them changed the industry. The first was self-loading. Testing a diesel locomotive under load traditionally meant hauling it to a facility with a trackside load box, a resistor bank that could absorb the output of the generator while the engine was run up. That meant scheduling, moving the unit, tying up a track. The new design let a mechanic anywhere on the system flip one switch and load test the machine where it stood. The second was modular control circuits. Locomotive electrical systems of that era were nests of point-to-point wiring, and troubleshooting one meant tracing conductors through a cabinet with a meter and a prayer. The new units replaced much of that with plug-in modules and solid-state control. If a circuit misbehaved, you swapped the module and moved on. That system did not arrive by accident. It came from pressure applied by the railroad's own electrical engineers, working alongside the builder's people, because the railroad had decided its supplier was falling behind competitors on exactly this point. Remember that, because it becomes the punchline of the whole story. If you are enjoying this one, take a second and subscribe. We cover locomotive engineering and the decisions behind the machines every week. Now, did the impossible locomotive actually work? For about a decade, it worked better than anything else the railroad owned. These units were geared for 90 miles an hour, which was unusually high for freight power, and they were the first from that builder delivered with a system that brought the traction motor fields up faster on acceleration. The practical effect showed up in the timetable rather than the spec sheet. Operating officers reckoned that a set of these locomotives could take a train across the 1,200 miles between Nebraska and Utah, roughly 45 minutes faster than any other power on the roster, at the same horsepower per ton, purely because of how hard they came out of curves and slow orders. Crews noticed. Getting called for a train with one of these on the point generally meant you were going to have a good run. The cab rode smoothly and was quieter than its contemporaries. There was one small tell that gave the game away. When these units were coupled behind an ordinary locomotive, they accelerated so much harder that they would physically shove the unit in front of them. and the walkway plates between them came back dented every time, and the railroad leaned on them without mercy. The fleet averaged around 22,000 miles a month in service. Within 5 years, most of the class had passed 1 million miles. Over their working lives, they averaged roughly 2 million miles each, which is a figure that very little contemporary freight power came close to matching. At the peak, the hottest merchandise trains ran with 3 of these locomotives, and 1 round trip to Southern California was assigned 4. That is more than 26,000 horsepower in the lead on a train of ordinary boxcars because the schedule demanded it. Only 2 units were lost during regular service, both to wrecks. One went on the grade in Southern California in 1974, the other in southern Wyoming in 1978. Both were stripped for parts and their frames sold for scrap. So if they were that good, why were they all parked by 1980? The answer starts underneath, at the place where the design had made its one genuine compromise. The fuel tank was not bolted to the frame. It was part of the frame, a structural member carrying a share of the load. That saved weight and complexity. It also meant that when 8,000 gallons of diesel sloshed around inside a 98-foot span flexing over uneven track, the stresses went straight into the structure. The frames began to crack. Shop crews welded vertical braces between the side sill and the tank to control the flexing. The braces were undersized and their mounting bolts started popping. Cracks opened along the seams where the tank wrappers met the frame members. Underside inspections became routine, and by the mid-70s there was a standing instruction limiting how much fuel these units were allowed to carry, well below their designed capacity, simply to keep the loads down. Repairing one was a miserable job. The cracks were along the bottom, which meant welding overhead while the locomotive sat over an inspection pit, which meant tying up an entire shop track for days while the tank sat drained and the machine sat on house steam. And the deeper problem was the one every double diesel had faced. There was 2 of everything, and it was all packed into a car body that had been designed to save space. An inch of clearance in the wrong place is the difference between a 2-hour job and a 2-shift job. One veteran of the shops put it. Simply years later, nobody who had to work on them missed them. There was one more issue, and it had nothing to do with steel. These locomotives were unique in North America. Railroads regularly hand trains off to each other and run through with the same power, and Union Pacific's partners flatly refused to accept these units on their own rails. Nobody else had the parts, the manuals, or the trained people. The railroad tried to fix the reliability. In 1976, it launched a program at its Omaha shops to rebuild electrical components, generators, engines, and traction motors across the fleet, and ran a second round 2 years later. It helped. It did not change the arithmetic, because by then the same builder was turning out a standardized 6-axle unit in enormous numbers, and Union Pacific had hundreds of them. They were newer, they were simpler. Any railroad on the continent would accept one. When the freight recession hit at the end of the decade, the choice was not difficult. Through the summer of 1980, the fleet went cold in batches, first to yards in Iowa and Nebraska, then to Nevada, then finally gathered together at a storage site in the California desert where dry air could hold off the corrosion. The newest units were 9 years old. They almost had a second act. When traffic recovered in 1984, the railroad found itself holding trains for want of power, could not get new locomotives delivered quickly, and could not negotiate a trade and deal for the stored fleet. So it started pulling them back out. 25 went back to work. 15 more were found unserviceable and retired outright, stripped to keep the others running. It did not last. The surge faded, the reliability problems returned, and by the spring of 1985, they were finished. One unit made the last regular freight run in May of that year. Around that time, somebody in Salt Lake City spray-painted a message on the highway viaduct pillars near the railroad's north yard, asking the company to save the whales and save the 6900s. Here is the part that makes the whole story worth telling. The locomotive that killed the Centennial, the standardized workhorse that railroads bought by the thousand, and that still hauls freight today, inherited its electrical system almost directly from it. The modular control circuits, the solid-state logic, self-loading, which became standard equipment on every locomotive the builder produced from then on. The experimental machine that the industry said should never have been built was, in the end, the test bed that made the ordinary machine possible. The X in its model designation meant experimental, and the experiment succeeded so completely that its results were absorbed into the mainstream and the original was made redundant by its own offspring. And the chief mechanical officer who forced it through? He retired in 1971, pushed out in part because he insisted on designing locomotives instead of simply buying them. He He was gone before the last unit of his fleet was delivered. He was also right, though not in the way anyone was measuring at the time. 13 or 14 of the 47 still exist. Most sit on display in parks and museums across the country, from Nebraska to Utah to Mexico City. One shell spent decades on a short line in South Dakota, gutted for parts, before preservationists started moving it toward a proper restoration. And one of them still runs, kept alive first by the railroad's own heritage program, and later by a preservation group, which makes it the largest operating diesel locomotive in the world by a margin that nothing built since has threatened. Railroads are not sentimental. They are among the most ruthlessly cost-driven businesses in the world, and they scrap what stops paying without ceremony. Which is exactly why the occasional machine like this one matters. It was not built because it was efficient. It was built because a group of people looked at the accepted wisdom of their entire industry, decided it was wrong, and spent 13 months and a great deal of money proving it. They lost the argument. The standardized locomotive won, as everyone said it would. But the thing that won was carrying the impossible machine's electronics in its cabinets, and it still is.